Good morning, everyone, and welcome to CAR's August seminar. Today's speaker is Dr. Suman Majumder. Suman is currently a postdoctoral researcher in the Harvard T.H. Chan School of Public Health. He obtained his PhD in statistics from North Carolina State University, and his research focuses around spatial statistics and its various applications. Many of you are aware of the current interest in improving the modeling of smoke during fire events, and Suman's statistical method is particularly relevant here. It is the basis of the blending utility currently being deployed into Victoria and Tasmania inside AQVX. And with that, I'll hand over to Suman.
My talk today is titled Statistical Downscaling with Spatial Misalignment. It is an application to wildland fire PM 2.5 concentration forecasting in the state of Washington in USA. Before I begin, here's a shout out to my team for this project: Yawen, Brian, Susan, and Anna. What exactly is downscaling? Well, typically downscaling is associated with improving quality of forecast at a high resolution based on a second source of information, typically of lower resolution. And along with these two, there is also a relationship that needs to be determined between the two. Sometimes this relationship is known, sometimes this is unknown. A fairly typical example of downscaling would be a global climate model forecast. Global climate model forecasts produce forecasts for the entire Earth, but it's not at a very high resolution. Say you can get forecasts for a country, however, knowing the temperature or the average temperature for the entire country doesn't really help you. What you really want is the forecast in your locality, in your city. So what you really want are local forecasts. So how do we get local forecasts from global climate model forecast? Well, we need a second source of information. So most of the time, this is some geographical information. For example, if your city is located near the sea or far away from the sea, towards the equator or towards the pole, what's the elevation of your locality? Based on this information, we know how temperature will vary because it's a physical process, and we know how that changes with these variables. And so using those physical processes and the relationship between these geographical information and the temperature variable, we can get local temperature forecasts. And that's a typical example of downscaling. So what exactly is statistical downscaling? Well, it involves one source of data that is typically a model-based forecast. And then the second source of information is also another source of data. Most of the time, it's a ground station observation, monitor observations. And a relationship that's unknown. The relationship between these two sources of data is typically unknown. And we use statistical models to establish an empirical relationship. It's empirical because it's data-driven. We don't know if it's true or not, and we have no idea. We let the data figure it out itself using the statistical models. And that's what statistical downscaling is. Our motivating example here is this. This is the PM 2.5 concentration in a log scale in the state of Washington on August 22nd, 2015. So the background here is a model-based forecast. It's called a blue sky model that forecasts every 24 hours. And so this is all the PM 2.5 concentration. And then these dots are the monitor stations and the observations in those monitor stations. Now, these monitor stations are, some of them are permanent, some of them are temporary. That's why there are some missing values here and there. And then there's a lot, you can see there's a lot of monitor stations here in a very small place, because that's where all the big cities are, as compared to here. Although there is definitely much higher activity here, as you can see. And August is actually wildfire season. This is mostly the forest here in Washington, and that's why there's so much concentration of PM 2.5 here. And why this particular case? Well, this is from 2018. So this is the Seattle skyline on a beautiful sunny day in June. 2 months later, it's August and it's wildfire season. It's already starting to get polluted, and just a week or so later, you can barely even make out the skyline. It's that bad in Washington. And so it's not just the visibility that gets hampered, it's also human health, public health that is at stake here, because PM 2.5 has a really long documented history of causing illness, short-term, long-term, both. And it's severely crippling to human health. And that's why the EPA in the US has these monitor stations to monitor the PM 2.5 levels and to advise the public accordingly. However, this model that EPA uses works pretty well in the East Coast, not so much in the West Coast, where it is actually a very big hazard. And the model EPA currently uses, it uses a linear regression model to correct the forecast in a post hoc manner. But that rarely accounts for spatial misalignment. In fact, almost no downscaling method accounts for spatial misalignment. And what I mean by spatial misalignment is, consider this scenario where this image is your original forecast. However, this image on the right is the forecast, is the actual observation or how it actually turned out to be. At first sight, you may not notice any difference between the two, but if you look here, this peak is missing, so the whole forecast kind of got shifted towards the right here. This has been stretched up, while this arm is outstretched here as well. So that's the kind of error we're talking about when we say spatial misalignment. That's it's somehow distorted the image. It's a distorted image of this original forecast, and we want to figure out what that distortion is. And the way we do it is warping. So the idea of warping is pretty simple. It's you have an image that's a template image. So this is the PET scan of a human brain, of a normal human brain. And suppose you have another image. So this is possibly a template somewhere in the book. And possibly you have another PET scan. This is possibly of a patient. But due to some clerical error or the patient moving their head, your image is a little distorted than what it should be. And so in order to check whether this scan is normal or not, by referencing to this image, you first need to match these images. In fact, you first need to make sure that you can even match these two images. And you don't typically know how to do that, and warping is how you do that. For warping, what you need is a set of reference points. So you know that these points have to be here, and maybe they are not in here. So what warping does is ensures that these points match these points, and the idea is to figure out what transformation would match these points with these points. And once you figure that out, you use that transformation to make them compatible, and then you can always match and say whether these two images are the same, if the brain is normal or not. So the idea is the same for our case. For our case, this is the image that we need to distort. This is the original forecast, whereas this is what we see. We don't even see the whole picture. We only see these little dots of points. But we know this is the gold standard. This is the template. And what we have to do is match the values at this point to match the values at this point. So we need to figure out the transformation of this that would let us match all the values at these points with this. And that's the goal of warping. In the end, we want a map like this that maps one location to another. And this map is what we're calling warping. So each map here, each arrow here point is, the end is one location, the arrowhead is another location. So that's a map from one location to the other. And it doesn't have to be something so simplistic or something as global as just a rotation. It could be anything. So the statistical model in use here looks like this. So YT of S is the manifestation observations at time t and location S, while X stands for our forecast at time t. And instead of looking at location S, we look at a warped location S. So this W of S is that mapping that we talked about, the warping function that maps one location S to another location that is W of S. So instead of matching the observation of the forecast of S with the manifestation observation at S, we match the forecast of X with the forecast X at W of S with the manifestation observation at S. And we add an intercept term here that varies spatially. This is just to account for the extra PM 2.5 levels near the cities compared to the wilderness. And since that level can vary, we want this bias to vary as well, spatially. And then there's a scaling correction as well. There is an error term that's just noise. That's the term our model cannot explain. But apart from just this warping, there is also this tilde, which signifies that we are not just using the X itself, we're using a smoothed version of X. So we are using smoothing on top of this warping as well. What do you mean by smoothing? Well, consider this as your original forecast. And this is a smoothed out forecast. The idea is to filter out the local noises. See, there's a lot of local variability here that is just not there here, or compare this to this region with this region. So the idea is to make sure these local noises die out so we can get a more clear idea about the pattern of the plumes. And note that the scales do not necessarily match, and that's just because of a particular smoothing technique that we use that's called spectral smoothing. So in spectral smoothing, assume that the variable x is like a white light, and we know that can be broken into different components. Each component has information about different wavelengths or different frequencies. So for example, red has the highest wavelength and lowest frequency, which means lowest frequency means really long range information, whereas for violet, it's really short range information. So just like that, X is broken into multiple components here. Some of them has information about long range stuff, while the others have really short range stuff. Visually, this is what it looks like. This is the original forecast. This is white light. And then these are the rainbow. So the first component that has information about really long range stuff. So it's really, really smooth. There's no local noise, so to say. The next one has a bit more local noise, but it's still smooth. And as you go along, you see, for example, here in component 5, it's basically just local noise. There is no long-range information whatsoever. So as you go along, these pictures become more and more grainy, and it only has more and more local noises. So by that logic, component 8 should be really, really grainy, but the reason it's not, it's smooth. And the reason is for spectral smoothing, we use a lot of sines and cosines, which behave really similarly to near 2 pi as they do near 0. So that's why it's a little smooth. But that doesn't really pose much of a problem. Now, the good thing about is this decomposition is exactly like light. If you combine all of this together, you get back the original plot. But we don't want that. We want a smoothed out version. So to do that, we weight, let's say the first 3 components, we put really high weights on these things. And the rest of them, we put almost 0 weight. What that does is all this information, all these local noises die down when you take a weighted sum of these things. And as a result, you get a much smoother picture. But that also means the scales can get messed up as a result of this smoothing. But fortunately, we have a beta parameter to minimize, to take care of that. And that's all the complications of our model. Once we fix on a model, we do as any scientist would do. We do a bunch of simulation study. So for a simulation study, we take the original forecast, we introduce some smoothing into it, we introduce some warping, some distortion like this, for example, and that's how we generate our data set. So here, for example, you can see that this place has been shrunk down a lot by this warping. And so sometimes we use smoothing, sometimes we don't use warping either to get this data set, just to try different scenarios to see how our model performs. I'm dumping a lot of information here in this one single table. So let's go part by part. This blue box here is basically how we toggle different settings. Whether we use a warp to generate the data, whether we use a smoothing to generate the data, whether in the data generation process the intercept was actually spatially varying or not. how many monitor stations are there in our original image. These are all the factors that we consider in designing our study. And then on the right, see these green boxes, these are our performance metrics. MSE is mean squared error, while CRPS is called continuous rank probability score. So the difference between the two is MSE is a performance metric for point estimator. So you give an estimate, you have a true value, you compute the squared error difference between the two, and you're done. But for CRPS, it's not just the point estimate. You also have to give an entire probability distribution for the prediction. It's called a prediction distribution, or since we are doing Bayesian modeling, it's called a posterior predictive distribution, or PPD. And so the idea is there's an empirical PPD based on the data for the training, for the test data, and then you have a predictive data from your model, predictive distribution from your model, and you actually match those two distributions themselves to compute the CRPS. And then this particular column in both cases is the full model that has both smoothing and warping. Our component models are just a simple linear regression model that's used now. Then there are some component models where you have only smoothing but no warping, only warping and no smoothing as well. And so the wide message here is the model works even when there is no warping and smoothing, or really pretty well, especially when they are there. We are really, really good compared to the other models. And about the warp estimation, so this is one of the works that we tried out for simulation. It's really simple. So the first case, we had only 25 monitors. And in the second case, we had 100 monitors. So as you can guess, with 100 monitors, it's a lot easier and the estimates are much better. This is another work that we tried. It's a little more complicated than the last one. As you can see, even with 100 monitors, we're having a little hard time to catch it perfectly. It works with 25 monitors. So, but these are all expected. So these are the takeaways from this simulation study. The model works pretty well, even when there is no warp or no smoothing. More monitor station locations always helps in estimating. And then the more complicated the warps are, the harder they are to capture. Once we're done with the simulations, we proceeded towards applying it on the data. For the data application, we have 4 competing models. These are the same as we mentioned last time. Simple linear regression model, and then a full model with smoothing and warping, and then component models that have only smoothing and only warping. And we have about 35 days worth of data. So for each day, we take the first 18 hours of data for training and keep the rest 6 hours for testing. The reason we only use 1 day worth of data at a time is because the forecasts are run daily. So in all likelihood, the warping itself changes daily. And so it doesn't make sense to use more than 24 hours worth of data together. The results tabulated are pretty simple. Well, all the models work pretty much decisively better than the simple linear regression model that's used. But within these, we see the smoothing model has the lowest MSE. But if you go down to this row for CRPS, you have a really reverse story of what you have here, which is a little baffling. So we figured the difference must be because of the entire distribution not just the point estimates. So we took a deeper look into those PPDs. So the means estimated are pretty much the same for the three models. And that's why the MSE doesn't differ so much, but the only difference comes from these standard deviations, which are higher for a full model. We also see that the warp-based models are a little skewed. So skewed means it's not necessarily symmetry around zero. Whereas kurtosis, this having higher kurtosis means it has higher, thicker tails. Which means more and more uncertainty in these models. And so the question naturally arises, is that normal, is that usual, is that something you would expect? And so let's look at this case. So I apologize if these points may not be very well visible. So we consider one point here, the edge of the fire. There is a lot of uncertainty here. How much of the PM 2.5 is going to roll in, whether it will roll in. So that means the PPD should really have high, thick tails. And that's what we see here when comparing the PPDs actually. So this red one is the full model, and it has much thicker tail than the smoothie model, which is the blue one. Whereas if you consider the case for a point here, that's smack dab in the middle of the fire, so there's definitely going to be PM 2.5 concentration and not much uncertainty about it. So we see that is the story here. All the models have pretty much similar tails, and they are not very thick either. So that basically tells us that the full model does a really good job of not just estimating these values, but also providing an uncertainty estimate for them. And so as a summary, I'd say we incorporate smoothing and warping in a downscaling method. And the smoothing only model was great for the data as a point estimate, but the full model provides much better yield. Thank you.
All right, thank you very much, Suman. So I'd like to open it up to questions now. I haven't had any in the chat yet, so I might ask one of my own. Suman, could I ask you to briefly explain a little bit more about some of the warp plots that had the different colored arrows and what the different colors mean and how we can tell when it's performing well and when it's not?
Right. That's a great question. Let me get back to the video, or I can actually move to PowerPoint actually. So share my screen with you. So the different arrows here are just because of significance. The red ones means that the warp here is actually significant, whereas the green ones mean they're not significant. Now, when I mean significant, it's statistically significant. So what that means is whether this warp is here or there is really no warp here, the output won't change much. That can be confusing because then you can say, well, I can have a different map and have the same output. And the answer is yes, the warp is not necessarily identifiable because suppose you have all zero values here, everything here is zero, or it's the same number. Then it really doesn't matter how you shuffle those numbers, how you shuffle the places of those numbers, it's all still going to be zero. So that's why the warp is not necessarily identifiable. But this significant or statistically significant warp means at least these location changes are important, so that we can make a better forecast. Does that answer your question?
I think so. Thank you, Suman. Our next question is from Martin Cope. He asks, is it possible to fix a subset of locations in space, i.e. the fire locations at the source of each smoke plume?
If you want, here's what I understand. You want to, instead of using, let's say, so instead of using these monetization locations, you want to fix, you want to use the fire sources as your fixed points and use those for figuring out this work. Well, that may be possible if we have data for that. So it's definitely an option, but we need to have the data here to be able to pull that off. So, like for example, here in this picture, here we actually had the full picture here, and so I could put three points that I want to be fixed points. But in this case, we don't actually have the full picture. If we had, continuous monetization locations all over the place, then we could definitely use those fire starting points as fixed points and use those to compute the work. But that like the problem as it is defined here, that may not always be an option.
Thanks, so I think Martin might be referring to, say, using satellite hotspot data so that we can be quite confident where the actual origin of the smoke is, but say we leave the origin in place, but we move the rest of the plume around.
I see. So you wanna, I see. So what you really want is to add some restrictions on the warping function itself so that it doesn't change some certain points. So that can be done. So if you use a prior that forces the warping function to change only at certain places and not change at the other places, then you can do it, but it will require some modification of the how we model this process. But it can definitely be done.
Thank you. Our next question is from Jeff. He asks, our Australian fixed site monitor network is relatively sparse compared to the USA. Do you have any general comments about the data requirements for measured, and he says, gold standard data?
Typically, I mean, as we saw in the simulation, more monetization is always better. But if you don't have that many monetizations, so what you actually need to do is play around with the method, with the parameters a little, and sometimes it helps to use informative prior. So priors that actually make use of some information you have about the general process. So you can tune the priors to be a little more informative, and that actually generally helps with the convergence of the chain. And also, when you don't have that much data, you probably have to run the chain much longer. But it's theoretically possible. Practically, it just takes more time.
Thanks for that. I might ask a follow-up question of my own on that topic. So this is related to applying this method in a near real-time sense. So
yeah.
there are a few issues that have arisen in doing that, and one of them is with us having fewer observations over sometimes larger areas. One issue that's popped up is non-convergent behavior.
Right.
So I guess I'm asking a general question about how practical you think this method is to applying it in a near real-time sense. And by that I mean to be able to get results within, say, a few hours that would let you act upon them. And how that would scale as how the computational requirements would scale as we do introduce more monitors.
Well, introducing more monitors, it's somewhat cubic in nature in the number of monitors. However, like for our example, the number of monitors here is like 55 for each time point, and then you have like 18 hours worth of data. So that's roughly 900, a little over 900 points. So inverting that isn't that much of an issue. So, but yeah, increasing monitor station observations does increase your time complexity almost cubically. However, the good thing is if you have more observations, you probably need to run a much shorter chain. So there is that trade-off in there. So it's not impossible that if you have a lot of data sets, or a lot of monitor station observation, it might be easier for things to converge. And as for the real-time application, well, the thing with Bayesian methods is, especially with MCMC method, they always take a lot of time. You could alternatively model this in a frequentist framework, but that would require a lot of optimization tool as well. So you'd have some convergence issues in terms of optimization convergence issues there as well. But as for real-time application, it might be doable because at least whenever you have just smoothing or just warping, those models converge pretty fast. When you have both smoothing and warping, there's really a lot of parameters that you have to take care of. And that's why the convergence takes that much more longer. As for, yeah, so for real-time application, if you have more data, it might actually be doable to do this in 3-4 hours. But if you have to run it really, really long, then obviously that's not a good way to apply it in real time.
Well, thank you very much, Suman. So I might just allow a few moments, and if anyone else wants to ask any questions. There being no further questions, I'd like to thank Suman for his presentation today.
Excuse me, Josh, could I just ask one more question? It's Jeff here.
Yep, go ahead.
I was just wondering that last comment about there's some computational efficiency from running the smoothing and the warping separately. Would it be useful to run smoothing and warping separately, then combine them using some other approach to overcome any computational, problems, or would that just lose the value of the method?
That's really an interesting way to look at it. We really haven't tried, combining the results from a smoothing and a warping separately. It might be a little difficult after you do a smoothing because whenever you're smoothing, you're really throwing out some information, local noise or whatever, but that's really throwing out some information about it. And then warping also introduces some amount of smoothing in there. And so what I think would be the most difficult part is to appropriately put them together in there. But yeah, that's definitely an avenue of extension or worth looking into that if you can put them together in a meaningful way.
Thanks very much, Suman.
Thank you very much again, Suman. I've found that very interesting. On behalf of all of CAR, thank you for making the time to give us this presentation.
Thank you very much.
Okay. So that concludes this morning's seminar. A recording will be made available on the CAR website at a later time. Thank you.